My name is Alexandria Udenkwo. I just graduated from the University of Maryland, Baltimore County with a degree in physics. And I will be going into a PhD physics program at Washington University in St. Louis. This summer, I worked with my mentor, Jason Kay, on a numerical solver for NCA type Green's functions, where we built a numerical solver from scratch in Python. All right. So our model is based on the Anderson impurity model. And with the Anderson impurity model, you can think of a lattice. And in the lattice, there are lattice sites. And at each site, there are 4 occupation states that it can be in. There can be no electrons. There can be an electron with a spin up, an electron with a spin down, and 2 electrons with one being in spin up and one being in spin down. And these electrons hop from lattice site to lattice site and experience Coulomb repulsion. On the right, we see a picture of an electron configuration of the Anderson impurity model. This specifically is a quantum dot setup where this quantum dot right here can be considered one lattice site. And we see here on this quantum dot, there are the 4 occupation sites where we have no electrons here, one spin up, one spin down, and then like one spin up and one spin down. And then these leads connect this dot to other electrons so that these electrons can hop in and hop out. Consider one lattice site where one is an impurity, and the rest of the sites are the environment. We are interested in 2 specific equations: the retarded Green's function, which describes the occupation of the impurity site over time, and the self-energy sigma r, which describes the environment, the effect of the environment on GR. So applying the non-crossing approximation gives us the Dyson equation, which gives us a relationship between the Green's function and the self-energy. In the time domain, our Dyson equation looks like this. And then applying a Fourier transform, we are given the Dyson equation in the frequency domain, which we see is much simpler. And then we have the spectral function, which is a sort of density of states function, which is the imaginary part of the Green's function. So in order to actually test our numerical solver, we look at a simple test problem, where in this simple test problem, we equate the Green's function to the self-energy with a constant c squared. And this is the simplest model for our self-energy. And this allows us to solve the Dyson equation such that we get an analytical solution for the Green's function, which is given here. And we see here, this is the analytical solution, where this is the imaginary part of GR, or the spectral function, where we see it's a nice semicircle. So this is the test problem in which we are going to test our numerical solver. So there are methods that we went through in order to make the foundation of the solver, and I will show you the results for them. So there are 3 methods. We have staying in the pure time domain, going between frequency and time in the mixed frequency and time domain, and then going in the pure frequency domain. The pure time domain we didn't go into in this project, but if you're interested, my mentor Jason has a paper, a fast time domain solver for equilibrium Dyson equations that you can look at. We particularly looked at the mixed frequency and time domain and the pure frequency and time domain, where sort of the mixed frequency and time domain was sort of a base where we start the program and then we extrapolate, from that we extrapolate the pure frequency domain. With the mixed frequency and time domain, we see more simplicity compared to the pure frequency domain, and the cost, we have O(n) log n compared to the pure frequency domain, where we have cost that depends specifically on features in the test problem we're looking at, which is really interesting when we introduce adaptivity, which I will talk about later in my talk. So in the mixed frequency and time domain approach, we have this iterative approach where we start with, where we start with the spectral function. So we start with a guess solution for the spectral function. And then we inverse Fourier transform that solution into the time domain. And then we apply a Heaviside function in order to get the Green's function in the time domain. And then we use our example problem the Green's function is equal to c squared times the self-energy to get the self-energy in the time domain. And then we fast Fourier transform into the frequency domain, and then we solve the Dyson equation to get the Green's function in the frequency domain. And then we take the imaginary part of the Green's function in order to get the spectral function, and then we do this iteration process over and over until we get our desired spectral function. Here on the left, we see after 1,000 iterations our numerical solution for the spectral function. And then here on the right, we have the error when we're comparing the analytical solution of the spectral function to our numerical solution. And we see that this error flattens out to 10 to the negative 1, but we're interested in machine precision, which is 10 to the negative 16. And then we have the pure frequency method, particularly non-adaptive. In the pure frequency method, we don't necessarily have to worry about switching between time and frequency. We just have to stay in frequency, which simplifies the steps. And so here we have 2 steps where we just have to worry about our example problem for the self-energy and then solving the Dyson equation. After 50,000 iterations, we see this is our numerical solution for the spectral function, the imaginary part of the Green's function. And we see here, comparing the analytical solution of the Green's function to the numerical solution, we see erratic convergence towards machine precision after 50,000 iterations. Now, I did say for this method, the pure frequency method, as well as the mixed time and frequency method, these are both non-adaptive. And what I mean by this is we did both of these methods on a uniform grid. But what we're interested in doing is taking this pure frequency method and applying an adaptive scheme. So what is this adaptive scheme? What is adaptive interpolation? Adaptive interpolation is an algorithm that automatically builds a piecewise polynomial interpolant that resolves towards localized features and functions. So our algorithm would put panels on our function of interest, and whatever localized features the function has, our algorithm puts more panels of smaller width, and as well as more points where the function is being solved. In particular, with adaptive interpolation, if we were to look at our test problem, our algorithm, our adaptive scheme would apply more panels around these cusps as their localized unique features in our test problem. And we're interested in applying this adaptive interpolation scheme to the pure frequency method. In particular, when we focus back on the Anderson impurity model self-energy, applying the non-proxying approximation, we have the self-energy sigma t is equal to delta t gr of t, where delta t is a hybridization function, which gives the action of the environment onto our impurity. And for the adaptive scheme, we want to stay in the frequency domain, which changes our self-energy from just being a division of our Dyson equation to a convolution in the frequency domain, according to Fourier transformation rules. So now we have to deal with a convolution with delta of omega, which could introduce more or less cost depending on the localized features within this self-energy. So that is the next steps that we're looking towards in this project. I would like to thank my mentor, Jason Kay, our collaborator, Corentin Bertrand, the Flatiron Institute, and the Simons Foundation. Thank you so much.
Great, thanks, Alex. Any in the room, any questions for Alex? So I had a question. When you were showing the error for the mixed time and frequency domain, right? It kind of makes sense to me that that error would go down as you do the number of iterations. You know, what is the feature, you know, that looks like it's at about 50? You get this bump that goes upwards and then back down. Do you know what? Do you have a feeling for what that is?
I would argue it's sort of a stabilization feature. So the sort of function, our guess solution sort of stabilizing towards the spectral function solution. So it's sort of just a feature that shows it's stabilizing towards that solution, but not necessarily to the point of machine precision. So yeah.
Okay, cool. All right. Are there other questions? Are there? Yeah, Oliver. Can you use your mic? I don't think she can hear without that.
Oh,
I can't
Can you?
necessarily hear the.
He's gonna try right now. Okay.
Okay.
If that seat it's not working,
Here you go. Use this. Use this.
Thank you. Thank you very much. Just a question regarding the mixed frequency and time domain. So is the point of this approach to avoid the convolution that you showed us in the end? Or why would one bother doing these Fourier transformations back and forth in every step?
Well, I would say we did the mixed frequency and time domain because, well, it's sort of a approach that a lot of people who are making numerical solvers do first. It's like sort of a basis before like you go into like more complicated schemes. So it's sort of like just the basis before like we go into the pure frequency domain, because that's sort of what we're more so interested in, because we can apply our adaptive scheme in that case. So yeah.
Okay. So you didn't have to bother about grid size adaptation and these sorts of things in the mixed approach, but in this pure frequency approach you had to do that. So it's more complicated in a way, even though the iterative procedure seems simpler than you had in your mixed approach. Is that correct? Or
well, I guess I would say with both of these approaches here, they're both non-adaptive. So they were both done in a uniform grid, but in our work right now and in our future work, we're interested in applying an adaptive method where we're shifting away from that uniform spacing. But yes, in the pure frequency domain, pure frequency domain scheme, the iterative approach is less complicated since we're just staying in the frequency domain. So yeah.
all right, nice talk. Thank you very much.
Thank you.
Okay. Any other questions? Okay. Are there any questions on Zoom? Okay. Why don't we thank Alex again